All right, let's get started. Hello and welcome to the stream. My name is Nick Larson, and this is us doing a little bit of AI and just hanging out and chatting. First off, a couple of things. I would like to throw a little shout out and a thank you to Ancient Coder, the Mike Jolly, and Riley Dom for the follows this past week while I was off stream but chatting on someone else's stream. Thank you so much. I really appreciate the support. Hope you can make it out. Hope you can chat. And let's go ahead and get started. First off, we should remember what we were doing last time. Definitely don't want that. We should remember what we were doing last time. And it is... we were stuck because the finding directions thing was totally busted because these landmarks weren't good. Let's take a look at how the landmarks were actually being selected and how it was generating the landmark heuristic. No definition for this. There. Go to definition. There we go. Okay, now you figured it out. Oh, and I forgot to change the name again. I'm really good at forgetting to change the name. Day 19. Update. Okay, great. You've updated. Okay. So the way that this was working, I've already updated this. Let's take a look at the diff. Fast. Working landmarks, diff. If we take a look at this, alright, previously what it was doing is we would take the landmark, we would build a reverse graph, and then what we were doing, no, we weren't even building the reverse graph yet. Okay, so I went through a couple of things here before I actually checked this in. Let's go over those. So first, what it was doing is it was just building a shortest path lookup, which is just like effectively what is it? Bellman-Ford, one single source shortest path to all other nodes. And then it was saying, okay, now just take the distance from the landmark to the start or to the current location and to the goal, subtract those, take the absolute value, and that's what the value of the heuristic was. And then it takes the max over all the different landmarks that we had. So as soon as this happened, we got a bad score. For we got a non-optimal directions is basically we ran the test and it did not return us the path that we know has the shortest cost. So we said, okay, I know something's wrong. And like intuitively in my head, I was like, it's got to have something to do with the directionality. And one-way streets have got to be causing problems here. So I couldn't figure it out while we were on stream last week, but I came up with like a pathological case where this generates non-admissible heuristics. The non-admissible heuristic was created because it estimated a value that was further than the real goal. And when it does that, it can prevent you from exploring a node that has a short value because it thinks that the path is going to be longer. And so I went back and I was like, all right, how do I actually fix this? Like, what is the problem with this? And I was going off of something that I had gotten from school, like an assignment. And one of the caveats of the assignment was that it treated all of the road segments as bidirectional. It was an undirected graph. So there was no such thing as one-way streets. And this works just fine in an undirected graph once you understand the real goal. So I went back and I read the paper that all of this came from. And when I was reading the paper, one thing really stood out. And the thing that stood out was that the landmarks have to follow this thing called the triangle inequality. This is the T in ALT for the ALT algorithm. And the way that that works is, let's just bring up the paper, right? That's the easiest way to do this. The paper would be at Scholar, and you want ALT algorithm. And then you want to view the paper. Okay. Zoom in, make it bigger so we can all see what we're looking at. All right, and one thing that really stood out when I got further into it and started looking at it is the concept of how you actually calculate the landmark heuristic. Landmarks. All right, so the way that a landmark works is you do exactly what we said, is you calculate the distance from the landmark to all of the other nodes. And then you also have to calculate... Oh, hey, what's up? I see you there, Mike Jolly. Good morning to you as well. What time is it where you're at? Did I miss you by a long time? No, I only missed you by a minute. There we go. That's not too bad. Oh, not nearly morning. That's cool. So what is that? Central time? Central time. Yeah, I'm on the East Coast. I live in Roanoke, Virginia. I just finished my lunch. I was like 3 minutes late. Yeah. So are you familiar with A-star search at all? Oh, that's cool. What part? I used to launch rockets in Alabama quite a bit. All right. So A-star search is really like nice. Okay. All right. So let's take the classic example. Let me open this up here. Do 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 do. Romania graph. Artificial intelligence. All right, images. So right here is and you can't really zoom in on it. Well, I hope you can see that. Okay, so pretend that you have this like map of roadways, right? And the idea is you want to get directions from point A to point B given any 2 points somewhere on this graph. And you want to find the optimal way to get there. Now, the way that you consider things to be optimal, we're just going to assign each edge length a cost value. And this can be, related to the speed limit, to, the average speed on this road during this time. If you're taking a flight, it could be like, the wind direction, whatever it is, you come up with some sort of way to assign values to each of the edges in a graph. And then what you want to do is you want to find the minimal cost path between any two nodes. And the one thing that's super important to understand is that the minimal cost path is not necessarily the shortest path in terms of number of hops. Like, for instance, the classic example here is Arad to Bucharest. It's shorter to go from Arad to Sibiu down here to Remnisu, Vilcia? I'm making these words up. I have no idea how to say these. And then to Petetsi, and then to Bucharest. Whereas it's a shorter number of turns per se if you go from Arad to Sibiu to Figueres to Bucharest. there's one less stop along the way, but it's more cost effective to go this way. And so what we want to do is we want to make a really big graph, like a huge graph, like say the entire world and all of the roads in the world. And then we want to say, what is the optimal way to get from here to there, right? So that would be like, let's go to, check out maps, and then let's zoom out so you can't see exactly where I live. Okay, there we go. And then let's say you wanted to go from like Philadelphia to New York, right? So from Philadelphia in here, and then to New York. There's a shitload of roads, excuse my language. There's a ton of roads. Somewhat smaller version of the traveling salesperson. No, it's pretty different than traveling salesperson. So traveling salesperson is like, I've got, a bunch of these points, and I want to find a way to go through 10 of these cities and then make my way back home in the most cost effective way. And that's the way that you approach that problem is notably different. Doing that, framing that as a search problem would be expensive for anything but really small graphs, and even really small graphs might still be pretty expensive. But yeah, I mean, in a sense it's like that, only think of it as like one leg of the traveling salesperson problem. We want to solve one leg of the traveling salesperson problem for how to get from this place to that other place optimally. And so, yeah, like if you take even New York, let's just zoom in on New York, right? In New York, there are tons of roads. Look at all these little square squiggly roads, right? And let's say I want to go from here and I want to get directions to where I used to live, 85th and 2nd, right about here. And this is what I want. I want it to give me directions from how to get from the start to the finish. And notice that it has to follow. There's a lot of one-way streets in New York, so you have to follow along one-way streets. So basically, that's the whole problem. And the way that we do that is using graph search. And graph search, just to give you a really brief introduction, let's just take a big screenshot of this so we can draw on it. Like this, like this. Like this. Let's go to Paint. Zoom in on Paint. Expand canvas. Oh, there we go. All right. And then let's move this. Okay. All right, so let's say, let's make this thick so we can actually see what we're doing. All right, so the way that it sort of starts is, let's say you start here, and what you do is you explore your neighbors, right? From here I can go to here, or I can go to here, or I can go to here. And if I go to here, then I have traveled a distance of 75, and I have traveled a distance of 140, and I have traveled a distance of 118, right? That's the easiest, most naive way to do this. And then we say, okay, give me the shortest one, and from there, let's see where else I can go. And then I say, oh, I can go to Oradea, maybe. And then it's like 146. That's how much it cost me to get here. And then that was the only place I haven't already been. So we don't finish exploring that. And now 118 is the smallest number. And so we say, all right, from 118 we can go here, and we say, all right, that's going to be 229. And then we're like, okay, 140 is now the smallest, and from this one we can actually go to two places. So we go and we explore both of these, and this ends up at, I don't know, I'm just going to make these numbers up at this point as fast as I can. 239, and what is that, 220? And then we just keep doing this. We say from Oradea, oh, we've already visited this one, so we don't actually explore this. And then we say, okay, we got a 220, a 229, a 239. So from here, we now explore this, and this ends up being, I don't know, 300, something like this. And what you can see is that it's going to end up exploring all of these like side places, and it will actually get here, prior to it finding the best goal. So even after you explore the goal, you have to keep exploring in order to find the best goal until you have reached the goal with until all of the numbers, the minimum number in your queue, is a greater than the minimum number it costs to get to here. So I hope that makes sense. And what we see here is we explored all of this crap, right? And that's expensive. We don't want to explore all of this. We certainly don't want to come down here and explore all of this, because we can pretty much tell from looking at it that it's not going to be the best way. Of course, we don't really know that. So what we're going to do is we're going to come up with a way to sort of estimate that. And the way that we're going to go about estimating that is, again, this will be our start and this will be our end. And what we're going to say is just give me something called a heuristic. Let's guess how far we are from the goal. So from here, and that's what all of these numbers are over here on this side. And what we're going to say is we have this new function, f of x equals g of x. G is the total cost that we've gone so far. That's what we were calculating in the last one for each of these nodes. And then additionally to that, we're going to say that the value of a node is also plus this thing called h of x, which is right now is going to be these values over here. And I'll explain a little bit more about that once we sort of walk through this and just sort of see how it works. So from a rod, we look at a rod and we say, okay, 366. So this is 366. That's what's in our queue. We pop that off. We go here, we go here, we go here, because those are the neighbors. So Zerend, and this was 0 plus 366, and that's how we came up with 366. So now Zerend has 75 for g of x, because that's our path cost to get there so far. And then we also have to add in h of x. So h of x for Zerend is 374. So we have 374 plus 75, and that ends up being like, what, 460-ish? And then we have Sibiu. Sibiu is 140 plus 253. That's like 393. Yeah, 393. And then we have Timisoara, 118 plus 329. That's what, 430, 47. 437. 437. All right, and now what you'll see is that the first node that we're going to expand is actually on the right path. And this is sort of the idea that we were hoping to achieve by adding in this heuristic value of guessing how far we are from the end. It makes the ones that aren't on the right path have a much higher value, and so we don't explore them very quickly. And we explore the ones that are more likely to be on the correct path a lot earlier. And so if we do this again, we'll see that we go here and here, and then it turns out that, you know, this ends up being a little higher, so I think we have to explore this one. We never end up exploring this one because that is higher than the actual goal value. I do think we explore this one time. We explore this, this, and this, and that. And I believe those are the only ones that get explored. But you see we cut off 1, 2, 3, 4, 5, 6 explorations just by having this heuristic, this really, really simple, naive heuristic. And the way that this heuristic works is it's just a straight line distance from Arad to Bucharest on a map using, like, the, what do you call it? A great circle equation. So this seems to be the key point right here, right? This heuristic function. You need to know two things about this heuristic function. One, it has to always underestimate the real value. If it ever overestimates the real value, then we would start taking these non-optimal paths a lot more, and we would end up exploring a lot more of the search space. And additionally, we can end up finding a solution that is not optimal. So it must underestimate. Straight line distance is the absolute smallest distance between 2 points that you must travel, right? If you have to curve at all off of that path, off of that straight line, then you're just adding distance. So it's a pretty good bound. And that's the one part of it. And then the second part of it is it needs to have this property that it is monotonically decreasing, meaning that if we add in some additional space, like as we get closer to the goal, the heuristic value always goes down by at least as much as we moved toward the goal. And if that's not true, then you're right back in that situation of you will find the non-optimal solution almost every time. Both of these things happen to be true for this problem and for this heuristic, so it works out just fine. And so what I did first was I implemented. Let me go ahead and just get it running here, and I'll just give you a little demo. First thing I did, Twitch. I need a terminal. New terminal. Alright, cd space fast.webapi.net run. Loading up the map data. This will only take a minute or so. Web API, map controller. Which city are we doing? We should actually output the city that we're doing. That would be great, wouldn't it? Loading map data. Plus city name. Loading map data. Based on the size, I'm going to guess this is Lima. Properties, startup. New York. No, it's New York. Great. Okay, let's go take a look at New York because we were already there. All right, so what we want to do is say localhost 5,000. Whatever. Do your thing. And then let's go find New York. All right. And so now we can do, basically exactly what we said, somewhere from down here to somewhere up here, and boom, there you go. You get it right there, plotted on a map, the best directions. Now, mind you, the way that this is working is entirely on distance. It's not taking into account the speed limit or, the traffic over time or anything like that. And that's why you're going to see different directions being suggested than what is suggested here, where this one has traffic and all of that crap. So mine is just going on distance, but if we zoom in enough, you will see that 3rd Avenue is not a one-way street. If you zoom in enough, you will see, like right here, that it does respect one-way streets. I don't know if you can see this or not, but there's a little bitty arrow right here saying that this one goes this way only. And so, great, we built this thing using straight line distance that even on a map with 708,000 total nodes, we were able to find the goal almost instantly, right? And that's pretty awesome. Let's go ahead and there you go. Every time you click on this, it takes you from the last place you clicked to the next place. And you can see it goes really fast. And this one, you got to go all the way over there and then come back. That's pretty crazy, right? That's pretty crazy. It's like, why is it like that? I don't know. That's pretty crazy. So if we go and take a look at how long it's actually taking to run this, you can see that it's taking about 54 milliseconds to run this search, and that's just on New York. The data set for this right now is about this area right here, right? So it's pretty large, but what I'd really like to be able to do is say, like, get me from New York to Los Angeles, and it should be able to do that just as fast, or maybe even faster, right? So if we say, like, New York to Los Angeles, like, it ought to be pretty fast. And that's the goal. I want to be able to figure out this, like, 2,800 mile trek almost instantly. That's what I want to be able to do. And so that's That's obviously not going to happen if we scale this problem up. So what I decided to do was take a look at a new heuristic. So straight line distance is pretty good, except it can get you into some trouble in places like this where there's just tons and tons and tons of roads. Because if I want to go all the way from the bottom to all the way at the top, and let's just take a look at that. If I want to go from all the way at the bottom to all the way at the top, straight line distance is exploring all of these different nodes all over the place. Actually, that one went pretty quick, didn't it? Let's try something from like over here to Newark. There we go. There we go, 159 milliseconds for that one. Because there's so many different roads, and it's going to expand. I'm like holding my hand in front of the map. But basically, I can do this. I can show you. Take another little screenshot here. And then let's go ahead. The way that it works is it's basically like exploring this and then exploring this and 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 this. And then it starts going this way, right? And what it ends up doing is doing something sort of like this. But you can see that it gets fatter and fatter back by the start and starts accounting for a lot of space that it has to look at back here. And so the goal is to come up with a better heuristic. And the idea being that a better heuristic won't have to explore nearly as many of these states out here on the edge. Let's choose a different color. It won't have to explore. It'll be a better heuristic will explore more like this. Like very, very skinny and directed all the way out here. And that ends up being enormously faster because there's a ton of individual states out here that you have to check. And the way that I decided to go about this was using a thing called landmarks. Let's take a look at landmarks. Landmarks are cool. File, open recent. Landmarks. Okay, so the way that landmarks work are basically we're going to take a point. These red points are what we're going to consider landmarks. And then we're going to move this up so that it draws on top. And then we're going to take this and give us a nice fancy purple. What you do is from this landmark, you literally calculate the value to the shortest path to every single other node in this graph. Like this, like this, like this, and probably, oh, actually we already did that one. So this would be the shortest path to every single node from this node. And then we do that for all the landmarks. We do it for this one as well, and this one would end up with a different color, like say orange. And we say, okay, here's the fastest, the fastest, the fastest, the fastest, the fastest. Then here, then here, then here, then here, then here, right? And so what you end up with is basically a lookup from a node ID to the exact distance to every single other node in the graph. And again, that can be quite large. In this example graph that we're using for New York, there's like 800,000, 700,000 nodes. And that's quite large. And what we want to end up doing, let's go ahead and zoom back. All right, the intuition as to why this is valuable is, let's say we want to get from the green node to the blue node. Well, it turns out that for one of these, probably this one up here, what's going to happen is the optimal path to get from here to here is exactly this path, which includes the path that we're trying to estimate the length for. Did my stream freeze? Uh-oh. Hey, there we go. Okay, it seems to be back. I'm not entirely sure. Yeah, there we go. Okay, seems to be back. Wow, what happened there? Did I hit like a blip or something? No idea. Anyway, so the intuition is this landmark includes two distances: the distance to the first node and to the second node, and those paths contain the actual shortest path that we're looking for. So the way that a landmark works is you take the second node and you subtract the first node. And what that ends up giving you, the value of the shortest path to the landmark and the value of the shortest path to the landmark, and the difference of those gives you the exact path length that it is that we're looking for. So like that's the intuition. And then you end up using more than one landmark because depending on the direction that you're going, not everything is so clean. Like for instance, the shortest path to there was up here, and the shortest path to down here is this one. And so these don't overlap. You can still get a good estimate from this, a better estimate. It's just it ends up being not perfect, but it's still ideally going to be better. And last week when I was working on this, I did a really poor job of implementing it, and I was just sort of going over right now. Does all of this make sense, by the way? Or is anything else that you want me to explain? The way that I implemented it last week was actually incorrect. And so this was me going over it to sort of show how I fixed it over the weekend because I spent a little more time looking at it. And I ended up finding a solution. This was me taking a look at a paper from, when I was in school learning this stuff. And it says, oh yeah, take the absolute value. Well, it turns out this is only true in undirected graphs. And I just sort of missed that point when I was reading through it. And when I went back to read the original paper, it showed me how to do it correctly, which is you have to calculate the distance from the landmark to both of the nodes. And then you also have to, in the reverse graph, calculate the distance to the landmark. And you take the difference of these two things, you take the max over those, and then you take the max over all of your different landmarks, and that ends up giving you your best score. So I got this into here, but I didn't actually put it into the graph, and I want to put it into the graph and see like how much better the search is after doing it this way. And so that's sort of where I'm at. And then hopefully this number of like 159 is going to end up being a lot smaller, right? If we just keep going back and forth between these two, right here, we see that it's about 110 or so going from left to right and about 160 going from right to left. And once I make this switch so that it actually uses the landmark heuristic, hopefully everything just works a lot better. And that's the plan. So now what I want to do is get the node locator. And I'm going to cough, so give me just 1 second. Okay. This is Havershine. This is what I don't want. And then there's this other trick, which is I don't know which points to use for the heuristic. So I kind of have to figure that out. And the way that I want to go about this is to basically, I think, just say something like locations. I want to basically select random locations is what I want to do. How do I get random locations? I don't know the answer to that. I am getting these locations from the nodes. Let's call this private static finding direction state array landmarks. You know what? I don't need to be creating this heuristic every time. We can just pull the entire heuristic up. And then we don't have to recalculate the heuristic each time. Oh no, we do have to calculate the heuristic each time. Yep, nope, we do. The reason being is that the heuristic has to take into account the goal location. Landmarks. I guess we could implement it separately so that it doesn't. Maybe? Maybe? Yeah. Okay. We can calculate man. A few questions. Hit me up. This is Kitten Ivy. Am I reading that right? Kitten Ivor. It's like really blue on my screen, like exceptionally blue. Do you put these vids up on YouTube? I sure do. They're all up on YouTube. In fact, let me find you the URL. You can find everything actually on my blog. Right here. Oh, Kitten Lover, I got it. Do you make playlists per paper or area like minimum spanning tree? No, I haven't so far. I have only been working on this project for about 4 weeks, and streaming in general for only about 5 or 6. So almost everything on it is in this vein. There were 2 different problems that I went for. The first one was the end puzzle problem, and then the second one is this map graph problem, this finding directions problem. So everything sort of falls into those 2 buckets. But I'll definitely take your suggestion. I'll take your comment as a suggestion and start putting together some playlists. I think that's a good idea. And also, this is a little out of date. I didn't get the stuff on there that I did at the very end of last week. So I'll probably update that later on today. All right, we're going to have to change the way that this heuristic works so that we only have to calculate it one time. Because if I have to pop the goal... yeah, never mind. We can do one thing like this. That's not what I wanted to do. Func finding directions state finding directions state double, and then this is going to be heuristic double heuristic. Absolutely. Thanks for coming to hang out, by the way. If you have any more questions, by all means, ask me, and I will be happy to interrupt myself, because that's what this is about. This is just a learning experience. This is a learning experience for me, and hopefully for y'all, and that's that. All right, so now what I want to do is say var landmarks equals select some random nodes. Nodes dot order by. Now let's do equals enumerable dot range. I don't want to order them by because that'll just take too long. So instead, what I want to do is say range, say 1 to 4. I guess it doesn't really matter. 0 to 4. And then what I want to do is say dot select. I don't actually care about that. So we're going to say var random equals new random. And then we're going to say random. And I'm going to put in a seed here. 2019-02-27. Just for reproducibility. Random. And we want nodes. I can't index. I really just want to select 4 random ones. You know what? I'm just going to do this the hacky way because I don't really care how long it takes for now, and that's a problem. Performance is a problem we'll fix later. Nodes.orderBy or random equals new random 2019-02-27 random.next. So this is just ordering them randomly and then take, let's say 4. Dot. That's probably good. I want to say map controller dot double heuristic equals heuristics helper dot make landmark heuristic, and then I want to say make landmark heuristic double. Goal. Just gonna copy paste for a second. To do clean up this copy paste job. Make landmark heuristic double. We're gonna say finding direction state current and goal. And then I don't want this. I don't want this at all. That's what I want. And I want to return from 2 to 2, and this is going to be finding state double. All right, so now this takes in from and a 2, and this lets me just do this calculation one time. Double map graph. It also wants landmarks. Landmarks. There we go. Now I have a double heuristic. And now what I want to do is come down here and say double heuristic of from and goal. All right, and then let's come back up here. Let's put the original heuristic, which is going to be double heuristic map controller dot double heuristic equals goal. All right, and then we don't want that one for now. Okay. All right, this is perfect. I'm getting some sort of video error on Twitch when I try to view my own stream. I have no idea what that problem is. It's making it so that I can't tell whether or not I'm live. Let's just go to my home page. Yeah, I don't know what's going on. That's really weird. I hope the video is getting to them just fine. Maybe I just got too much going on with my computer. I got some sort of... Maybe it's time to restart my browser. I don't know. Fine for you? Great. Okay. Well, I'm going to keep rolling with it then. Only thing that's weird about it is I can't see myself. Okay. So what I just did was the original heuristic used to only say, from this location, give me some estimate. And now what I wanted to do is create something that says, from here to here, give me some estimate. With the idea being that there's a lot of calculation that has to go into that up front that I don't want to repeat. And I have to have a goal in place in order to just have the first one. So now I'm creating this one that has 2 inputs, and then down here I'm wrapping it with the one that just has 1 input, and always calls it with the goal. And so now that's it. We have implemented some random landmarks for New York City. I guess what we ought to do is put something in there that actually... That's one thing that I definitely want to do. Let's go like this. Let's say private static finding directions state array land map landmarks. And what I'm going to do is basically assign these, and then I'm going to create a little route that will show me where on the map they are, so that we have some sort of idea. And we can use that to sort of estimate whether or not it's actually giving us good values or not good values. Okay, so what I want to do is say, let's just call it landmarks. Landmarks. Let's call this landmarks. .to array. All right. Be explicit about this so that I can find it later. Okay, and then let's add in another thing here called get landmarks. HTTP get landmarks, and this is a public action result of finding direction state called get landmarks, and this just returns landmarks. Array. Okay, and let's put it in the right order so I can just toss them over there. Dot select new object. Nope, just a generic object of lat equals m.lat lng. And the reason I'm using lng here, that's what the Google Maps interface wants to use, and this just saves me a little like mapping step in the web code. m.longitude .to array, and let's just give it a class, private class. Actually, I already have lat long here, don't I? I do. New lat long. Okay. There we go. Now, let's go to the actual static map. And then what I want to say is go get me some function. Get directions. Function get landmarks. And same idea here. We just want to fetch map get landmarks response.ok response.json console.log locations landmark console.log of data. And then we want to say for each for let L equal alright, for L in let L in data. Oh wait, for I in data. I'm making this up here. Equals data landmarks. And then we want to create a map marker, which I'm guessing is going to be something like google.maps. Google.maps.marker of L. Const marker equals that. And we want to say marker.setMap map. And then I want to say get landmarks at the very beginning. So once this thing loads, add listener. Element center load initialize. I don't see initialize. There it is, initialize. So once the map is created, then just go get your landmarks. Let's see if that works. I have absolutely no idea if that's going to work. Let's kill this. Let's reload this. Let's go ahead and say New York. We had a thing up, didn't we? Let's go here. Just want it to be closer to where we are. New York. USA. And then let's put a little to do, pull this so we don't have to check it each time. Okay. It's going to load. It's going to call get landmarks. It's going to fetch off a request to this URL. All of these need to be indented. All of these need to be indented. It's going to fetch off, it's going to go get the JSON back. It's going to tell us what it is in the console. It is then going to actually create some map markers. And hopefully that works. Let's save it. Let's run it. Loading New York. All right. All right. There we go. Load it up. Get a little drink of water. Okay. You taking long enough? Oh, it's also calculating the landmarks now. I should put a little note in here. Say something like console.writeline calculating heuristic. There we go. So we know how long that takes. Okay, so it loaded this up. And now let's go load it up, and hopefully it gives us the landmarks. Ah, this .set values is not a function. Okay, well, did it give us back? It did. It gave us back some landmarks. That is awesome. Okay, it gave us back some landmarks. Marker. I'm gonna have to go check out the Google API. Google Maps JavaScript API marker. lat LNG map position. Oh, marker position map. Got it. Position map. Okay, let's make that. Position. FYI, on your home page, you have a link to the Pit of Success is a metaphor for tools that lead you down. The link is old and busted. Oh no. About the Pit of Success. Oh man, that's lame, man. I'm gonna have to fix that. MS has some other ones, but other people talk about it also. Yeah, I was linking back to the original post that it came from. Let's see. Pit of Success. Falling into the Pit of Success. I really don't want to put it. Oh, wait, here it is. Brad Abrams. There we go. They just moved it. And they did a really bad job of it because all of the styles are in it. Okay, I'm going to put a little note here to update that. Update the Pit of Success link. Thanks for pointing that out. I really appreciate it. Yeah, that's the one right there. Oh, wait, no, it's Brad Abrams is the person who came up with it. This is the one that I was looking at right here. There you go. Team Rico. Actually, I'm not 100% sure. Yeah, that's the one. Yeah, the format is completely busted. I probably use the link that you have. It's more readable. I think it's the same content. It is the same content. Okay, yeah, I'll use the one that you got. Thanks so much for that link. I really appreciate that. I will get that updated later today, right after the stream. All right, position L map map. Where was I looking? JavaScript API. Marker dot set map map. I don't really want a title on it. My lat long position. Google dot. Oh, new Google dot maps. Okay. I have more confidence in this. Let's try it out. Ooh, what's up? Okay. Perfect. So these are the landmarks that it randomly chose. And now what we're going to do is we're going to see if going from over here to over here, like we were looking at earlier, can now be done faster. Oh. Cannot read property. URL internal server error. No. Cannot read internal server error. Give me the error. The given key was not present in the dictionary. Oh yeah, that's right. That's right, now you have to deal with this. You could link to the original on the web archive. You know what? That's not a bad idea. That one's more likely to stay there. Instead of having to constantly chase this around. Alright, that's good. Okay. So I got the map markers on there correctly. Now what's happened is it has randomly chosen places that are not accessible. Okay. What we're going to do is change. This is something that's sort of been a bug for a while and I've needed to fix it. What we're going to do is we're going to change this to say if lookups dot toLandmark dot contains key from dot node ID and lookups dot toLandmark dot contains key to dot node ID. What we're going to do here is say double to L equals from L equals 0. Equals 0D, 0D. Then what we're going to do is say to L. Actually, we'll just do it like this. And then sort of the same idea. What we're going to do is instead we're going to say from and then we're going to copy this and we're going to put that there and then we're going to say from landmark. All right, and then we're going to say double. Oh, actually, we don't even need to do this. We just say double max equals 0. And then we can say max equals math.max of max and this. And then we can say max equals math.max of max and this. And then we can just return max. Alright, what this does is it says I will return a value of 0, which is always a valid heuristic, or I will return the maximum of where these locations can be found. And also, I think, ideally, we would do some pre-processing. Okay, yeah, this has to be done better. Okay. And let's copy this as well to go here. Let's go to the map controller, and what I really want to do is say something along the lines of to do find a better way to choose landmarks. And then let's go ahead and just let it choose new ones each time, I guess. Let's try this one more time. C, build, run. Wow. Heuristics helper 37. Oh, goal. Goal. And technically, as long as this one has a value, no, we can't. Okay, we'll come back to that. Okay, let's try that again. Load it up. Hopefully this time it gives me some more interesting landmarks, and regardless of which landmarks it has, hopefully this time when I run it, it will choose some better ones. Calculating heuristic. Here we go. Here we go. I mean, here's sort of here we go. It's a little slow. It's a little slow. So what it's doing right now is for each of those 4 points, it is calculating the distance to that point from every other point and the distance to every other point from that point. So what we did is we took the size of the graph and then we basically multiplied it times 8 because we're using 4 of these things. So it uses a lot more memory, like a lot more. Let's see, where would it be running? It would be running in here. Yeah, about 2.6 gigs, 2.7 gigs or so. All right, let's try this again. Okay. You give me something about how you can't load correctly, that's fine. Those are our points. Now, let's see if we can do what we wanted to do from earlier, which is get from Queens, Jamaica. Where's Jamaica? Sure. From Flushing to Jersey City. Whoa. Not faster. Still 186. Let's go back to Flushing. Okay. Let's choose a couple of different locations. Let's go from like, there we go, 20 milliseconds from there to there. 41. I'm not sure that this is going faster, to be honest with you. It's kind of hard to tell. I think overall it's fast enough for me to be happy about it. I don't want that. That's kind of cool though. Let's see, how far away can we go? All the way down here? Bloop, bloop. That's good. That's really good. Okay, second idea for how to make this faster. There are, if we zoom in here, and we take a look at this, it turns out that there are an enormous amount of little bitty edges in here. Like, see, if we zoom in on this, every single, like right here, it's really difficult to see, but there's a little angle difference right from here to here. And right here, there's a point. And there's a little line segment that goes from just here to here. But you notice this is just, right here, this is just a street going in one direction. That's sort of a bad example. Let's choose something more like this. All right, so something like this, where you're going to end up having like 3 or 4 points in here. And what we want to end up doing is not having to search all 4 of these points individually. When we notice that there are points that are in the middle that are just part of one whole street, we want to collapse it down and just have the like intersections effectively be the points, and then have all of the points in between the intersections just be collapsed down. Oh, look at that. Cannot read property C of undefined. What did I do? Not sure. Map.js7. Oh, that's not good, is it? Console. I mean, it seems to be working, so I'm not super concerned about it. Maybe I just clicked on something silly. That was kind of cool also. Notice that there's different one-way streets, so it takes different highways. That is kind of fun. And then you get these like little loop-de-loops because it's actually following the highway. I do just have way too much fun with this. I really have to stop like playing with this and actually try to get stuff done. Okay. I mean, that is a lot of fun. It just is. It really kind of is just a lot of fun. Landmarks work. They're still expensive. We need to make this faster. Okay. Okay. Okay, so the way that we're going to go about this is we're we're just going to look at the points when we have our full map, and we're going to have like a compressed map stage of the processing that collects. So basically what we're going to have is something like, give me a new one, Control Shift in, no, Control in. So basically what we're going to have is something where it's like, here's a point, 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 here's a point. So basically what we're going to do is now we're going to say something like, this goes to here, 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 this goes to here. No, don't do that. This goes to here, this goes to here, and this goes to here. And what we would want to do is, this is an intersection, and this is an intersection, and this is an intersection, and this is an intersection. This is not an intersection, nor is this and this and this. And what we want to do is basically say that you have these unique lines that look sort of like, you have one that goes all the way through here is one unique line, another unique line, another one, another one, another one, another one. Okay, so what this would do is it would, and then let's put in, let's see here, giant green balls. So that becomes an intersection, an intersection, an intersection, an intersection. So we turn this graph that had 1, 2, 3, 4, 5, 6, 7 nodes into a graph that has 4 nodes. And that should be faster to search through. So let's go ahead and figure out how we're going to do that. What are your cases? If you have 3 or more points, you are an intersection. Yep. Okay. If you have 3 or more points, you are an intersection. If you have Is that true? This is points leading out. If you have All right, let's just think about the cases. Give me a new one. Okay. You can either 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay. It is very possible that you have 1 directions. I'm just going to put the directions for all the directions, okay? And let's make it black. Okay. So if everything is one way, you can have 0 things coming out one thing coming out or more than one thing coming out. In the case that you have more than one thing coming out, you are absolutely an intersection. Okay. Intersection, for sure. For sure. If you have one thing coming out, definitely not. Definitely not. And if you have 0 things coming out, definitely not. I think that's it. I think it's entirely based on the number of points leaving. Where you are the source and you are going to somewhere else. In those cases, you are an intersection. And we want to keep you. Right. Okay. What about coming into you? You either have 0 things coming into you. No, it's all about which directions you can leave. Okay, that's what makes an intersection. I'm pretty convinced of this. Guess we'll know in a minute. Defining intersections. Close this one. Reducing to intersections graph. And then that's that. Save. Explaining A star. Okay. Okay, so we want to process the map. This is going to be in the OpenStreetMap data helper. And what we want to have is something called compress map. Extract map graph. Finding direction state. So how are we going to do that? That's a good question. Well, first we can just do the compression and then we can worry about actually reconstructing the original later. I think that's a good idea, just to test out whether or not this has value at all. We're just trying to see if it improves the search speed. Okay, so let's say compress graph equals new graph. Okay. Nope. We're going to make a whole new graph. It's going to take in a graph. It's going to return a graph. and it's going to take in a graph. And yeah, you can't return null. Okay. Why is return not giving me coloring? I have opened it, I have closed it, I have opened it, I have closed it. Let's go with doo-doo-doo-doo-doo-doo. Okay. Loop over the edges. For each edge, if it has more than one node, neighbor, okay, okay. We've taken a graph. What we want to say is var edges equal graph dot enumerate edges. Var new edges equals oh no, I got it. Okay. Okay. Yeah, var new edges equal new list of OSM edge. And then I want to return graph new adjacency list weighted graph finding direction state double new edges. Var new graph equals var new nodes equals new hash set finding direction state. That's it. New graph, new nodes. Okay. All right, so the idea here is we're going to loop over all of the edges for each var. Actually, I'm not. I am? Let's see. Do I need a reverse graph here? Probably. Otherwise, whichever node I start with is just... So we're going to go over all of the nodes. And I need to build chains regardless of which one I start on. Yeah. Okay. Why am I not getting coloring here? This is really kind of bothering me. It's like it just decided to crap out on this. I don't know. There we go. A little bit better. I got some news. I have to have something wrong syntactically. No. Is it extract map graph? Reduce map graph. I don't know. I honestly don't know. Enumerable finding direction state nodes. All right. That's the new thing that I want to build. That's the edges. I want to build a reverse graph. I do. Because I can stop anytime I get to an intersection. Yeah, reverse graph var reverse graph equals graph helper dot make reverse graph of graph. Okay. Var visited equals new hash set of finding direction state. Now what we're going to say is, all right, for each var node in nodes if visited contains node, continue. And then what I want to say is get the neighbors. Get the neighbors. Var forward neighbors equals graph dot get neighbors of node. Okay. And then what I want to say is if forward neighbors dot, okay, if 0 forward neighbors, then end of road. If 1 forward neighbor collapse, if two forward neighbors intersection. If forward neighbors dot count what on earth is going on? Let's just to array it. It's not going to be too many. Using link. To array. Dot length equals 1. So only in the case that it's 1 is it not going to be a thing. In the case that it's 1, let's just have a thing called like probe. No. Probe of forward neighbors graph yeah, I think that's it. And what this should return is end and visited and path nodes. Okay, that's what I want to do. And the reason I need this, let's go with dist total weight path nodes. Okay. Private finding direction state double finding enumerable finding direction state and total weight path nodes probe, and this takes in a I don't know, is this something I even want to do now? I'm just like rethinking this because right now this only gives me intersection to intersection, but imagine you had like a roundabout or like a giant loop around a city and you were trying to get from, well, I guess there's going to be off ramps. You know, if you wanted to find like some house in the middle of a street, you'd still have some work to do. Is this worth it? The big question with everything. Is this worth it? I think as far as... I'm just kind of curious how much of a compression we get out of this. I'm curious how much of a compression we get out of this. Because there's no reason we couldn't augment the path. I have to think there's value here. Okay. Probe takes in a finding direction state node. Finding direction state. In fact, I just want to probe forward and probe backward. I don't even care about this. All that stuff can go in here. Okay. Node. And then we want the graph. Weighted graph. Finding direction state. Double graph. Okay. Why is this having trouble? Because that doesn't exist. Probe. No, seriously, what's your problem? An object reference is required for the non-static field. Static? That's a good way to do that. I have something wrong. I have something wrong. I have no idea what it is. Probe. Not all code paths returned. Okay, it seems to like this now. Okay, so whatever I did seems to have fixed it. Throw new not implemented. Just to get rid of the compiler error. And then I want to say this probes to one end. And then I say same idea, only we're going to call it beginning. Front. Start. Total weight. Back path nodes. Forward path nodes. And this is going to be reverse graph. Weight 1. Weight 2. Weight forward. Weight backward. And then the edge that I want to put in. Okay. If end equals start, This sucks because it found a loop. If the end does not equal the start, then the reverse graph, then the new edges. Okay. How about continue? Var edge equals new OSM edge. Start, end, weight forward plus weight backward. New edges dot add edge. Then we want to say for each then we want to say visited dot union with new hash set let's just call this forward path nodes dot to hash set and reverse back path nodes dot to hash set. Now we need some more helpers. Collection helpers dot cs using system dot link using system dot collections dot generic namespace fast dot helpers public static class collection helpers public static hash set t to hash set of t this i.e. numerable t source return new hash set t of source. Okay. All right, so what this does is it gets any edge we need a queue. Okay. Var q equals new list finding directions problem. Nope, state q dot add nodes first. We say while nodes dot count is greater than 0. What? What? method group. Okay, we have definitely identified that there is a problem. Nodes dot count. What the hell is going on? This is like 50% of coding, trying to figure out where the typo is. I honestly don't know. You want me to do it like that? Oh, Q. I don't want that. Okay. Q dot count is greater than 0. Var node equals, let's do a stack. Push. Dot pop. Okay. And then what I want to do is push okay. If node no, I don't want to do it like this. Thought that would be easier, but I'm starting to think otherwise. Yeah, for each node and nodes. Just go through them all. We don't need a queue. For each node and nodes. If we've seen it, then bail. The trick here is when you go backwards, the trick is when you go backwards, do I want to cut that off? I've already gotten the forward edge, and I know that there is only a single forward edge for that node. No, there could definitely be more forward edges. This just happens to be one forward edge. Damn, it's complicated. I should really be writing this on paper. All right. Well, it's 2 o'clock, and that's gonna end up being pretty much it for me today. What I'm gonna have to do is just sort of put a bunch of to-dos in here. I think, honestly, I want to go about this a little bit differently. I think, given a graph, I want to copy the graph, like just absolutely create a copy of it. And then what I want to do is create the reverse graph, and any node who has exactly one neighbor no, I want to go over each node. Yeah, okay, this is it. I want to create a copy of the graph. I need some way to remove. I want to go and find all of the ones that are intersections, and then I want to probe from there. I only want to probe intersections. If it's not an intersection, I don't want to probe it, because it will be removed by the intersection probes. Yeah, that's the right way to go about it. Okay. So that's going to be it for today. Thanks everybody for hanging out. Really appreciate it. And we'll see you tomorrow, same time, same place, right at noon. And that'll be it. I'll get my website updated in the meantime to post up the rest of the videos that I have forgotten. And also to fix up that one link on the homepage. Thank you very much for that, Kitten Lover. All right. Everybody have a good one. I'll see y'all tomorrow.